Okay, now we are going to talk about the theorems that we use to approximate probabilities. The first one is the law of large numbers. I'm going to do a brief introduction. So consider a sequence of IID random variables. IID, remember, that is independent and identically distributed random variables x1, x2, each with expected value mu. So that means the expected value of x1 is equal to the expected value of x2 and so on. And the expected value are equal to mu. The variance is the same, the variance of the first random variable, and the variance is equal to the variance of the random variable y, I for example, and this is equal to sigma squared, and so on. Now consider the sample mean of the first n of them. This n is called the sample size. The sample mean is denoted by this term, xn, and is equal to the sum of the first n terms, x1 plus x2, and so on until xn, divided by n, by the sample size. This is the sample mean. The sample mean is itself a random variable because it's a function of random variables. So if we have a random variable, we can calculate the expected values, variance, the distribution, and so on. The limit theorems we are going to discuss describe the behavior of this random variable, the sample mean, as the sample size n gets large. Okay? What is the expected value of the sample mean? Well, we can take the expected value of this random variable. By definition, this random variable is the sum of this random variable, x1 until x10, over n. And using properties of the expected value, we can take this n out of the sum of the expected value. And the expected value of the sum is the sum of the expected values. So this is the expected value of x1 plus the expected value of x2, and so on, until the expected value of xn. But those expected values, we also said, are equal to mu, right? So here we have the sum of n expected values, n times mu in this case. This is equal to 1 over n, and we have n times mu. And if we cancel this out, this is equal to mu. So the expected value of the sample mean is going to be the expected value of the random variables, that is mu. Okay, what is the variance of the sample mean? Well, the variance of this random variable, again, we can use the definition, is the variance of the sum of the random variables. And using the properties of variance, we can take this n out of the variance by this square, 1 over n squared, times the variance of the sum. But they are independent, right? The random variables are independent. So because they are IID, this is the condition, IID, they are independent. So the sum of the variance of the sum is the sum of the variance. So this is going to be the variance of x1 plus the variance of x2, and so on, because they are independent, right? And again, we are summing here, these variance are sigma squared. So we are summing sigma squared n times. So this is equal to n times sigma squared over n squared. We cancel this out. This is equal to sigma squared over n. So this means the variance of the sample mean is equal to sigma squared over n. Is equal to the variance of the random variables over n. Okay, now what happens to the variance of the sample mean as n is large, as n goes to infinity? Well, in this variance here, if we take limit here of n to the infinity, this variance tends to 0. So it goes to 0. Now, the formal definition of the law of large numbers says that the sample mean, xn, that is a random variable, this converges to the true mean, mu, the parameter that is a number, as n goes to infinity. So we know that the expected value of the sample mean is mu. But the law of large numbers says that this sample mean converges to mu as n goes to infinity. So the law of large numbers tells us that if an experiment is repeated a large number of times, that is n goes to infinity, the average value of a quantity of interest, that is the sample mean, should be close to its 3 to the theoretical average, the theoretical value. So we have two examples here. For example, if we roll a dice n times and we take the average is going to tend to converge to the theoretical average that is 3.5, right? The expected average is the possible outcomes 1, 2, 3, 4, 5, and 6 over 6. That is 3.5. That is the theoretical average. But if we do the experiment, if we roll a dice, for example, 1 time, we can take the number 5. If we roll 2 times, the average should be something, for example, 3.8, and so on. If we do many trials, the average approaches the expected average, right? If you can do the year-round experiment and you can prove that. Over many trials, the average approaches the expected average, the theoretical value. Or for example, if we flip a coin n times and n goes to infinity, the proportion of heads that we are going to observe converges to the theoretical value that is, in this case, is 0.5, right? So if you flip a coin 1 time, you probably get head. If you throw 2 times and take the average, you can take 0.6, for example, or 0.3, and so on. As you increase the sample size, that is the number of flips in this case, you are going to observe that the proportion converges to the true value that is 0.5.